Okay.
Nappy on the test.
Yes, in one form or another, definitely. Definitely. The reason we spend so much time elaborating on it is because probably about 1/3 of us will be taken out of this world by a malfunction of this system. Okay, it's a very common. It's a very common problem. So therefore, it's very important medically.
Very encouraging.
Well, okay, guys. If your parents didn't tell you this, you are going to die someday. Okay, all right. I'm sorry. Santa's not real, and you're going to die someday. It's just my job to be a total downer.
Yeah, I was having a good day.
I'm sorry, but maybe not. Who knows? Maybe you'll figure out how to live forever. But generally speaking, the leading cause of death is life. Okay. Okay, not to be too morbid.
I'm depending on that.
You're all young, right? So you get to be my age, and you get a little closer look at that, and it's like, whatever. Okay. So what we have here is some tissue. We've had some experience looking at histology. So this is some dense irregular connective tissue out here, and the fibroblasts, and then we get to these two structures right here. Okay. These are our vessels in cross section, and that's a vein, and that's an artery. They're quite different when you look at them. Now, some of the structural features that you'll find in every vessel, I'm just going to jump up here to this picture. We have a ceramic board or a rubber, I think it's actually a rubberized board in lab. It looks a lot like this, and you'll have a chance to look at that on Wednesday. So here we're showing you the vein, and there's the artery. There are 3 layers that every vessel has except capillaries, okay? And they're called tunics. Tunic means layer in this case. Okay? The inner layer is called the tunica intima, that's this right here. And then we get to what's called the tunica media, which is this layer between two kind of things that look like Swiss cheese, but those are elastic membranes. Right? Tunica media. And then we have this stuff out here called the tunica externa. Those are our 3 layers that we have. Intima, media, externa. All blood vessels have those, like I said, except for capillaries, where they really just have an intima. So if you look at those 2 things, which of those 3 layers looks markedly different between veins and arteries?
The middle one.
The middle one, the media.
Mm-hmm.
Yeah. And the artery, the media, is a lot thicker. Here, and the vein is much, much thinner. What type of tissue is that?
Connective.
No, that's not connective tissue. Let's go back to here. Maybe you can tell me here. That's this layer here. You almost can't even see it in that picture. What type of tissue is that? Anybody recognize that? I think I heard it very quietly. It's smooth muscle. That's smooth muscle. Okay? That's what most of your media is. It's smooth muscle. Okay? One of the lessons we learned about histology is that your hollow organs have smooth muscle in their walls. Okay? Your blood vessels are a great example of that. Why do we have smooth muscle in the walls of our vessels? Is it for peristaltic contractions to push our blood around our body?
Yes.
Okay. No. What was it?
So you can contract, right?
It is so it can contract, yes. Constrict, we call that.
So
It's not to propel the blood around the body, but it's to maintain blood pressure. Okay? Remember, the function of arteries is to push back on the blood and keep the pressure up. Part of that is due to the elastic nature of arteries, and the other part is the muscles. Okay? The muscles contract on it a little bit and increase your blood pressure. We call that concept vasomotor tone. Vasomotor tone means that blood vessels, the tunica media of the blood vessels, i.e. the smooth muscle, is always being slightly stimulated to contract. And that's maintained by sympathetic stimulation of the ANS. We call that vasomotor tone. There's a center of the medulla oblongata of the brain that's called the vasomotor tone center. And it's always keeping out a certain amount of sympathetic stimulation to your blood vessels, so they stay slightly constricted. If that signaling gets messed up, you lose your vasomotor tone and you pass out. That's what a knockout is. If you get a blow to the face, it sends shock waves through the medulla oblongata, and temporarily that system breaks down a little bit and it loses the sympathetic tone of the blood vessels, and you can't maintain blood pressure, and you pass out.
And your blood pressure drops?
Oh yeah, it can drop to 0 actually, and then you pass out, and then one of 2 things happen. Either the medulla oblongata figures out what's going on and you recover in a couple of seconds and blood pressure comes back up, or it doesn't and your blood congeals and you die. Okay, so ordinarily that doesn't happen. Okay, so we got the tunica media here. Now this really, artery versus vein. Very, very easy to tell the difference, right?
Mhm.
So you know you're gonna have a test on the lab practical like that. I'm gonna show you a slide. I'm gonna have the arrow pointed at this and say, what type of vessel is this? You're gonna tell me, that's a large muscular artery. Or I'm gonna have a pointer over here and say, what type of vessel is this? And you're gonna tell me, well, that's a medium-sized vein. And we'll talk about how we can tell the differences in a minute. The other thing I want to draw to your attention here, the lumen size of these two. Okay? You notice they're running next to each other. In fact, they even have a kind of a common sheath around here. This is connective tissue that go around both of them to hold them in place. And if you were to dissect out blood vessels in a cadaver, you'd see that a lot. The blood vessels tend to run next to each other. They run in pairs like that. Like we looked at them, we just had a chance to start looking at the models today, and I think you were mentioning how the fact that the arteries and the veins frequently have the same name even, because we have a subclavian artery and have a subclavian vein, because they're in the same place and they're both beneath the clavicle, so there you go, that's why they're called that. And they're running next to each other. Now, if you were to dissect this out, the veins are a heck of a lot larger than the arteries. Their veins are much, much larger. It doesn't look like that here because the vein wall is very weak. So when you preserve them and you section them, the veins tend to collapse in on themselves. Okay? Whereas the arteries have more elastic tissue and more muscle, and so they tend to stay more open when you section through them. So when you see these in histology slides, frequently the artery will be this nice round thing, and the vein is this collapsed in, ugly looking thing next to it that's even hard to see the lumen. But if I were to fill these up like water balloons, this one, you'd see that that lumen is actually 2 or 3 times the size of that lumen. Veins have a larger lumen than do arteries. Now, what do you think has to accommodate for more blood flow, a vein or an artery? It has to accommodate for more blood flow.
Artery?
Okay, so the artery, why?
Because the lumen is smaller.
Well, having a smaller lumen would seem to be less blood flow to me.
Right.
That's what
What are you
pushes
asking?
the blood.
Which one has to allow for more flow? So, all right, if you're saying arteries have less flow, you're saying veins have more flow.
Okay.
Wouldn't they be equal?
Ah, okay, this is the better answer. Yeah, sorry. Okay. Yeah, arteries and veins, you have the same volume of blood, right? So you got to be able to carry the same amount. Well, as we'll get into a little bit in the coming lecture, the pressure in these two is very, very different. Okay, and we've mentioned this before. Arteries are under high pressure. Veins are under low pressure. Now, in your house, if you have plumbing in your house, you probably know what happens when the pressure is low. Flow goes to nothing, you know? If you have 3 showers in your house and you all try to take a shower at the same time, the pressure is split 3 times. So whatever that pressure was in the one shower, you turn on the other 3, and I have a well, and so, as I've tried to teach my kids over the years, you can't, have a sink on, you can't flush 3 toilets and everybody take a shower and do laundry at the same time. It doesn't work that way. There's only so much pressure to go around, so you gotta kind of take turns. So this causes a problem, right? If veins are under low pressure and arteries are under high pressure, and we have to accommodate the same flow, the only factor we can change is the diameter, okay? If you got low pressure, the way you get more flow is to make it wider. So veins are wider. Veins have a larger lumen than arteries to accommodate the same amount of flow at a low pressure. Okay? Veins are wider to accommodate the same flow rates as an artery, but at lower pressures. And there's another little trick the body uses. You actually have more veins than you have arteries. I don't know what the ratio is, 1.5 times, 2 times as many, but you have more veins than you have arteries, also to accommodate the same amount of flow. Now, with that said, something I told you about when we discussed Starling's law of preload and venous return, I mentioned something at that time. Veins can function as a reservoir for your blood. Okay? Because you do have more of them and they're easier to stretch, you have about 60% of your blood volume at any given time in your veins. So they actually do accommodate for more blood than do the arteries. And this can be a little bit confusing because there's a difference between the volume of blood that's in them and the flow rates. The flow rates are pretty much equal. But the actual amount of blood in the veins at any given time is higher than it is in the arteries. It's only about 15% that's in the arteries, but it's flowing very rapidly through there. 60% of the blood volume that's in the veins, but it's flowing more slowly through that. But since it's a larger volume, the flow rates, the total amount of blood we move per time is the same.
Well, where's the other 25? In the heart?
Capillaries, heart and then in the different organs. And off the top of my head, I don't want to get the percentages wrong, okay? It's like 12, no, like the heart is like 6 or 8%, something like that. And then the capillaries, I think, is about 15, somewhere around here. Okay. And then in this slide, I want to show you a capillary, but I don't think, if I remember, this slide doesn't have any good ones in it. Out of this material out here, you'll occasionally see a capillary. Relative to the size of the artery in the vein, a capillary would be about this size right there.
What's the purpose of a capillary?
What's that?
What's its purpose?
Oh, she asked, what's the purpose of a capillary? I'm glad you asked that. A capillary is actually the main functionary of the circulatory system. A capillary is where nutrient and waste exchange happens. Okay. Capillaries are always between arteries and veins. So we're going to talk at length about arteries and veins, about how we regulate flow around the body, because that's important, you know, how we control the flow of blood around the body. But when you get right down to it, for your tissues, it's the capillaries that matter. Okay? The capillaries what control bulk outflow on one side and bulk inflow on the other side of the capillary network. Capillaries are where we go from arteries to veins. So we talk about the artery side capillaries and the vein side capillaries. We call those capillary beds.
And you said they take waste out of the body?
So the capillaries do two things. They deliver nutrients to the tissues, and they take wastes away from the tissues. We call that nutrient and waste exchange. That's the job of the capillaries. All right. Well, let's see how much I want to get through this. Well, since we were talking about that, I'll go up to this slide. This shows you a diagram of how it's connected. There's the heart in the middle, arteries going out, capillary bed in the middle, and then veins coming back. Okay, so that's pretty straightforward, right?
Mm-hmm.
We have to go through a capillary bed most of the time to go from an artery to a vein. And I said most of the time because there are a few tricks we can use, okay? And let me outline the problem here. You have capillary beds in every organ, okay? You know, your reproductive organs. You have capillary beds in the heart, in fact, okay? When you talked about the coronary circulation, after we go through those coronary arteries, we have to get to what are called the myocardial capillaries, the capillaries that actually do nutrient exchange with the muscle tissue, okay? And then you go into the veins. That's true of any organ. In order to get the nutrients to the organ, it has to have a capillary bed. You have about 5 times the amount of capillaries as you do blood volume. In other words, you cannot fill all of your capillaries all the time. And if you did, you'd look like a tomato, okay? You'd be all swollen up. If every single organ were filled up with blood as much as it could possibly hold, maximally all the time, you'd need at least twice your blood volume, maybe as much as 5 times, okay? So clearly we don't do that all the time. And of course, you gotta stop and think about this. Think about like your house as an analogy. Do you use everything in your house that can possibly use electricity all the time?
My roommate does.
Some people, it seems to be a sport. They do try to do that. But no, generally you don't, okay? You're not running your water using appliances. You're not running your furnace and your air conditioner at max all the time. Every light in your house, every radio in your house, every TV in your house, every computer in your house, everything on max all the time. You don't do that, okay? If you did, I can tell you this. The circuit breakers in your house couldn't handle it, okay? You'd overload it, okay? And certainly the whole neighborhood couldn't do that, okay? If every house in the neighborhood tried to do that, the Illuminated company the whole branch would fail, okay? It can't support that. And your body's the same way. You don't use every organ to its maximum capability all the time. Because when you're doing that, that's when it needs its maximum blood flow. You don't do that. You're not using your skeletal muscles to the maximum rate at the same time as you're using your brain, okay? You're not using your reproductive organs at their maximum rate at the same time that you're using your kidneys, okay? Your kidneys are, not functioning fully, I don't know, while the uterus is trying to do something else. I think probably skeletal muscles and the stomach are an easy example to understand, okay? You're not using the blood supply to your stomach maximally when you're running a marathon because you didn't eat a turkey dinner. And likewise, if you eat a turkey dinner, that's not the best time to go run a marathon because your stomach's trying to digest that stuff. It's actually called gastric steel when you do that. That is why